we have now this afternoon another seminar, and today we have the pleasure to have here Dr. Valéry Lainey. He's a professor from the Institute of Celestial Mechanics and Ephemeris Calculation, IMCCE, of the Paris Observatory in France. And he is a specialist in astrometry, orbital integration, and generation of ephemeris of natural satellites. He is responsible for providing ephemeris of natural satellites for the Gaia mission, and also ephemeris of the Galilean moons for the JUICE mission. Valéry is also the coordinator of the IMCCE working group, that is a team from the International Space Science Institute, composed of experts from different fields related to planetary science, and the goal is to study giant planets and their satellites. So, as I said, it's a pleasure to have you here today, and Dr. Lainey today is going to give us a talk on astrometry unleashed, the Saturnian system. So, Valéry, please, the podium is yours.
Okay, thank you very much. So, as you know, the Cassini mission was really a fantastic mission for astrometry. It was a fantastic mission for a lot of things, for sure, and our knowledge of the Saturnian system had changed a lot thanks to this immense success of the Cassini spacecraft. And astrometry played an important role, actually, in the way now we are looking at the Saturn system formation, evolution, and so on. So astrometry, as you know, for some of you do know pretty well astrometry, you know, well, when you have observations, you need people, you need a lot, it's a lot of work. And in the case of the Saturnian system, actually, I was lucky enough to have really a whole team, as you said, the ONSLAD team. So I don't know if you can see the cursor on the screen, but all these people here are actually
yes, you can.
A lot. Okay, good. I worked a lot on the results that I will show you, and also our Italian colleagues from Bologna for radio science things. Okay, so I guess most of you do know what is astrometry. I assume so, but I have just a few slides to introduce the subject in case some of you do not know exactly what kind of astrometry we are dealing with concerning satellites. So, as you know, of course, astrometry aims at providing the position of solar system objects with highest accuracy. And in the case of moons, for instance, when you are looking from the ground, this is Himalaya, the biggest outer moon of Jupiter, and it's here actually, and you have stars in the background. You do know exactly, more or less exactly, where the stars are on the celestial sphere, thanks to Gaia catalog nowadays. And so thanks to that, you are able to, from the pixel position of stars, to go back to right ascension and declination. And so once you are able to convert pixel positions into angles on the celestial sphere, then basically you are able to determine the center position of Himalaya on the celestial sphere. So from a space, this is exactly the same thing. Actually, here this is an image from ISS. So this is the camera, well, the narrow angle camera on Cassini in a visible camera. And you can see here, actually, I think this is Rhea. And well, of course, biggest difference from ground is that now the disk is fully resolved, but the idea is still the same. You do have stars in the background, so trust me, they are here. You cannot see them really, just see the Gaia expected position. But we also have stars in the background. So from the star position, we're able now to know precisely where the camera is aiming into space. And then once we're able to do that, we're able to convert, once again, pixel into right ascension and declination. And in that case here, the only difference is that we're not looking for a photocenter here. That would be pointless. We'll basically try to fit an ellipsoid here onto the disk that you get here. And then the center of the ellipsoid should be related to the center to the center of mass of the satellite, or assuming that center of figure and center of mass of the satellite are the same. They are not exactly the same, probably maybe a few kilometers differences, but basically, I mean, it's good, close enough for what we're doing at the moment. Okay, so but this is just two examples here, but we can do astrometry with a lot of different ways. So for instance, here, if you have in mind the old times with photographic plates, well, that was exactly the same idea. You had satellites, planets, and stars in the background, and that we were playing the same game. The thing is that thanks to modern technique now, we are able to scan the plates with a very digitizing machine, very sophisticated and very expensive, actually, digitizer. And from that, we're able to get numerical images of these photographic plates. And then we can do the whole process now with Gaia star catalog and the modern technique for photocenter fitting and so on. So this is typically something that we're still doing at the moment at the Paris Observatory at Meudon, despite the curfew and all these kind of things. So we're scanning the plates with a new machine called NARO. We can also do astrometry using photometry, and some of you probably do know what are the mutual events. So here, I remind you that every 6 years, the Sun and the Earth are crossing the equatorial plane of Jupiter, which means that you are able to observe mutual occultation of one moon by the other one, like here, or mutual eclipses of one moon by the other one. So in that case, you will basically observe a light flux drop, and from this light flux drop, you are able to get an astrometric measurement of the two satellites. So basically, this is here photometry, but with astrometry measurement in the end. You can also do photometry for astrometry when you have star occultation, and these measurements are extremely accurate. Thanks to Gaia catalog now, we have very high accuracy on star positions, meaning that when we do observe a satellite occulting a star, we are able to determine in the end the center of figure of the satellite with very high accuracy. So this is something that Morgado et al. They published 2 years ago, and they get really few kilometers accuracy on the position of the photocenter of the center of figure of Europa. So a few kilometers. This is typically the kind of accuracy you would get from space, generally from space probe. So this is the same accuracy you can get here from ground thanks to Gaia and this kind of occultation. And so that's really great. Other techniques also, you have mutual approximation, so it's more or less the same as mutual events. You have two satellites are getting close to each other, but the difference is that you do not need necessarily to have one satellite occulting the other one. Basically, what you will measure will be, with time, the distance between the two satellites, and the distance will come to minimum and then increase again. And by getting a pretty precise timing, when they get close, well, provides you some astrometric information. You have also different, very completely different kind of measurements. So, for instance, you have the radar measurements. Some of them for the Gillen satellites have been published last year, actually, by Marina Bruzovic and colleagues. So here, this is the case of Arecibo radar measurements that were performed between 1992 until 2016, if I remember well. So the idea basically is to measure the round trip of a radio wave. And by doing that, you're basically measuring a time. So, and thanks to the time, and of course, speed of light, basically you are able to measure the distance from the Earth to the satellite with very high accuracy. And typically the accuracy, it's roughly the same as star occultation, so it's a few kilometers. The major difference is that with the radar measurements, you are measuring distances, while in the case of star occultation and classical astrometry, generally speaking, you are measuring angles on the tangential plane. So this kind of measurement here is completely complementary to classical astrometry. And last, we can also use spacecraft when you are looking enough to a spacecraft in orbit around some target of interest. when you have flybys, let's assume here this is Cassini and this is Titan flyby, clearly. When the spacecraft is moving close to Titan, its trajectory changes and suffers from a gravitational attraction of the satellite, which means that you are able, by monitoring the motion of the spacecraft, to determine precisely the gravity field of the moon, for sure, but also you are able to get a very precise estimation on the position of the center of mass of the moon also. It's very important. And it's probably, so this is here in that case radio science measurement. And in that case, probably the only measurement that do provide you center of mass, because all the other one, including radar measurements, they provide you center of figure. But here you're going to have center of mass. So eventually, when you get enough accuracy, you might one day be able to determine center of figure, center of mass displacement shift. But so far, I'm not able to do that on the Jovian satellite or Saturnian satellite. Okay. Since I'm talking about spacecraft, I would like to emphasize something that is very important, I think. Classical astrometry, and what I will present here, and the tools that I will show you, basically they are the same that I used by radio science team, and more generally speaking, they are the same from space geodesy. So whether you are interested in a motion of solar system objects, rather than natural objects or spacecraft, basically the technique is really the same. So you have you do have the same motivation in general. So let's consider once again the Cassini spacecraft. In both cases, classical astrometry or radio science, you do want to provide orbit and ephemeris for the whole astronomic community. So this is important. Of course, you want to provide very high accuracy of on the ephemeris of the natural satellites, but you also want to provide very high accuracy on Cassini spacecraft. You also want to study the interior properties of celestial objects. So I just show you the flyby of Titan by Cassini, and for sure one of the scientific interest was to emphasize the interior of Titan. So this is something that we like to do with spacecraft. But this is also something that you might do with classical astrometry, as you will see. You want also, in the end, to try assessing formation and long-term evolution of the system you are looking for. So in the case of Saturn system, again, as you will see, our vision of the Saturn system has changed a lot, both thanks to our astrometric measurements of the moons, but also thanks to radio science of Cassini itself. We also have the same asset because radio science is a mandatory part of the success of any mission. You want to know where your mission is into space, so you need really to have radio science data, radio tracking. So you do have this instrument anyway, and you also always, or most of the time, do have a camera with which you can do astrometry. So these instruments are part of the spacecraft. So they are here, and definitely we should try to use them as much as we can for science, and not when we can. Okay, so I told you this, the methodology was the same. So astrometry measurements provide you position into space. And the whole game is to be able to have a model that do provide you estimated position of this object with respect to time, and to be able to compare the computed position from your model with the observed one. And from the differences, of course, you're going to be able to increase your knowledge of the physical parameters you have in your model. And in the end, well, you are improving the knowledge of the system itself. So you need to integrate the equations of motion, evidently. So I may not really want to discuss all of them, but basically here this is the classical Keplerian part. And of course, you need to introduce the extended gravity field of the primary. So we do have a pretty good now estimation of the Saturn's gravity field, thanks to the grand finale and the final part, the Cassini mission. You also have mutual perturbations within the whole system. So of course you do have a lot of resonances between for instance, Mimas and Tethys, or Enceladus and Rhea. So mutual perturbations are very important between satellites. You also want to include the extended gravity field of the moons, so they are not just spheres, but of course sometimes you do know a bit more, especially thanks to these flybys of the spacecraft. You also have tides, which actually are very important if you want to assess the long-term evolution of the system. So you have tidal forces acting within the primary, but also within the satellites. And in the end, you also want to include general relativity terms. So basically, this is post-Newtonian potential. So generally, these terms are small, but they can be sometimes very important, and especially in the case of especially when you are looking for the motion of spacecraft, which get very high accuracy on the measurements. So anyway, generally speaking, you put them just to be sure that everything is fine here. But that's not enough, because if you get that, basically you're able to compare position with observations. But you also need to be able to correct your physical parameters that you include into the model, which means that you need to know the derivative of the state vector of any moon with respect to any initial condition here. And this means that basically you have another set of equations to integrate simultaneously that are called the variational equations. And in practice, this system is way more complex to integrate than equations of motion. So to say that in a few words, basically equations of motion computation is easy, and the very difficult part is here. And then you are using generally least squares fit. So of course you can have a lot of tricks I can include here, but basically this is least square. Okay, nevertheless, we do have differences between spacecraft and natural satellites. So first of all, spacecraft generally have polar orbit, while natural moons do have equatorial orbit. So moons have equatorial orbits because of the formation process. So that evidently they formed in the cloud that formed the planet itself. So basically, they are of course in the same plane. For the spacecraft, you do have a polar orbit because of mapping of the surface. So polar orbit is more interesting for sure, meaning that you are not sensitive to the same harmonic of the gravity field of the planet. So that's typically kind of complementary thing that you might expect in that case. The modeling also, data treatment are different. So probably the biggest difference actually between spacecraft and natural satellites is the fact that with natural satellites, and generally speaking, natural solar system objects, if you have let's say a century of observations, you will solve for only one initial state vector for the whole century. There is no reason to split the data arc into the data into a small arc of data. No reason to do that. For spacecraft, it's very different because you have a lot of maneuvers, so called wheel of loading. Sometimes you have drag pressure sometimes, especially, for instance, for Mars missions. And so in practice, you cannot solve for one state vector over, let's say, 13 years of Cassini mission. You have actually to use much smaller data set. And for each of these smaller data set, typically several days, you will solve for one initial state vector of the spacecraft. So, and you have to repeat that on each data set. So, meaning that it's hard with space geodesy to get long-term signal, but you will be very accurate on short periodic signal. So that's typically kind of complementary things between classical astrometry of moons, in our case here, and the radius science of spacecraft. And last, of course, observation accuracy is different. So astrometry typically few kilometers in the best cases, so star occultation or radar measurements, and many times it could be up to a few hundred of kilometers, which is more easy to get most of the time, evidently, while geodesy gets typically a few meters to a few kilometers. Okay, so let me show you here an example of great complementarity between these two kind of data set. So here, for space geodesy here, let's look at the sun that is raising tidal bulge on Mars. This tidal bulge actual direction actually slightly shifted with respect to the solar direction, because you have dissipation, so friction inside Mars, that provides a small time delay, and so you have a small angle here. Spacecraft here will basically be in orbit here, so once again, polar orbit or close to polar orbit, and they may be sensitive to this variation here of the gravity field, so basically the tidal bulge. And they do, and actually since several years, even more actually now, I think more a decade probably, we do have an accurate estimation of the love number of Mars. But spacecraft until today are not able to compute, to determine, this small angle here, this lag angle of the tidal bulge with the solar position, because it's too small. So it's pretty hard, because this means that to be able to measure this angle here, you should first get a very high accuracy on the tidal bulge themselves, and then looking for a small angle. Now, so basically with what called K2, so love number K2, so characterizing the tidal bulge, basically the amplitude. And from astrometry here, there's something different. So you have Phobos that is revolving around Mars, and as you probably know, Phobos is getting closer to Mars because of tides that it raises on the Mars surface. So basically, so the tidal bulge here now are lagging with respect. No, sorry, they are. Yes, I think the picture. Yeah, they are lagging with respect to Phobos direction. Because Phobos is revolving very fast, faster than the Mars rotation period. So in that case, Mars is getting closer. Phobos, sorry, is getting closer to Mars, and this means that from this change in semi-major axis, or I should say, actually, it's acceleration in longitude, you are able to determine here this angle. So looking now at classical astrometry measurements of Phobos, you are able to get an estimation of something that is related between the tidal bulge themselves and the angle. So in short, if the angle is small but the tidal bulge are important, you may get the same result, or let's say the same acceleration of Phobos, as if the angle was large but the amplitude was smaller. So basically, you are able to determine the K2 by Q. So that a combination of amplitude, tidal bulge, and the tidal angle. But since because of the spacecraft, you already get the tidal bulge amplitude, you are able now to separate both quantities, roughly, with some assumptions on frequency that I don't want to go into details. But you can clearly see that on this very simple example here, thanks to one of classical astrometry or radio science by themselves are not able really to get all the parameters we would like to get, but when you get all the information, radio science on one hand and classical astrometry, then you get a total global picture of what's of the physics you are looking for. Okay, so now example with Saturn, because most of my talk is on Saturn actually. So generally speaking, when we're talking about classical astrometry, probably people have in mind improving the orbit of the satellites. Which is true. This is something we want to do, of course, but we can do more than that. So sometimes you may have in mind, okay, we can also probably get the mass of the satellites by mutual perturbation. That is correct, but we can do much better than that. So I would like to emphasize here a few examples of things that we succeeded to do with just classical astrometry. So, right, so the first thing I would like to show you concerns actually the unimoons of Saturn, but this is also true for any moon, and especially the moons that are close to their primary, because generally speaking, they have a very elongated shape. And in that case, because they are not spheres, you have a torque that is acting from the primary on the satellite because of this distorted shape, and this torque actually will introduce a libration on the rotation of the satellite. So not the orbit. I'm not talking of the orbit at the moment. just talking about the rotation, and you do have an extra libration here. So of course here, I guess you know that all the moons close to their primary are in spin-orbit resonance, so they are showing the same phase to their primary. Of course, you have a slight libration here because you have an eccentric orbit, so you are not seeing exactly the same part of the satellite. We are seeing roughly 60% of our own moon, thanks to the eccentricity of the orbit of the moon. But you also have an extra libration, this extra angle here that goes like this with a specific frequency that is related actually to the distribution of interior of material inside the satellite. So looking at the rotation of the satellite and getting this so-called physical librations provide information in the interior of the satellite. This actually was done with the Cassini ISS data, Tiscareno et al. In 2009. They succeeded in quantifying the physical libration of epimeters. So this extra libration here, that is roughly 6 degrees. And thanks to that, they could provide some information about the interior of epimeters. And for the small moon of Saturn, probably the first question you would like to answer is whether or not they are homogeneous bodies, because that gets consequences on their formation. And you probably know that we suppose that this moon formed from material from the rings. So that's very interesting. But so it could do that for epimeters, but not for the other moons. And one thing you may want to try is to also determine this physical libration, not just from looking at the rotation itself, but looking at the feedback on the orbit because of the rotation physical libration. So this is something actually was very interestingly discussed for the first time by Valéry and Yoder in 1990, to the best of my knowledge, but applied only by Jacobson in 2010. So this means that for 20 years, this method was known, it was published, but not used. The idea here is actually to look at a very specific signal on the orbit related to the periapsis. And if you are expressing the periapsis drift associated with this physical libration here, so this is the A is the amplitude of the physical libration related to this momentum of inertia, well, you get some you get an extra secular effect on the periapsis. So the periapsis drift is going a bit faster or slower than what you would expect if you do not model the physical libration. I would like to stress this sentence in Valéry and Yoder 1990. I think this is very interesting. So I remind you that in the 90s, we had this Phobos 2 mission, Russian mission. We also had the legacy of the Viking and Mariner 9 mission. So we had already a lot of astrometric measurements of Phobos and Deimos. And they said that, talking about this term associated with physical libration, they could provide a more accurate estimate of the Phobos libration than direct observation of the figure oscillation from ranging to a lander if all effects acting on apse and node are accounted for and if the length is about a year. So basically they were saying that just look maybe at the orbit of Phobos and you might get something that is good enough to infer the interior of Phobos just by looking at the orbit. That's very interesting. Okay, so what I represent here will be basically to use this method, so to introduce this physical libration into the modeling of satellites and to use classical astrometry of Janus, Epimetheus, Prometheus, and Pandora, and to try to assess the interior of these bodies. So this is what we did. This is here an example of the data we had with Cassini mission. So this is here in pixels, so this is the residuals, astrometric residuals. So if you want to have an idea in kilometers, you can multiply by a factor, let's say, between 5 and 10, it depends. So let's say by a factor 8, and you get kilometers. So typically we have here we have 20 kilometers standard deviation on these moons. If you want to compare that, so with Hubble Space Telescope, so I'm sorry, this is here arcsecond, but it's more than an order of magnitude larger. So really, Cassini mission gave us a strong constraint on the position of the lunar moons that, I mean, really step forward to our knowledge on the orbit of these moons and also on the physics of these moons too. You can use this by using this data set. You can solve for the state vectors of these moons, the 5 moons, but you can also try to determine their mass. So I just would like here to show you. I will do the numbers here, but what is interesting here is that you can estimate the density, and the density you can see here. Atlas is the smallest one, and then they get bigger and bigger when you are further away from Saturn, and you can see the density is increasing. So those two ones, which are very close, they have a typical density of 0.6 gram per centimeter cube. Those ones are typically 0.47, 0.5, and here is roughly 0.4. So you can clearly emphasize this difference in density with distance to Saturn. So that's not new. Actually, that's something that was known already by Thomas Grupo, and here we succeeded in getting a smaller bar, but I think it's very interesting to know that. So but I told you, a classical astrometry can do more than masses. So let's look at the physical vibration that you can get with this method. So you can also solve for physical vibration. So once again, I don't want to go into the detail. I can do that at the end of my talk if you have questions. And you can see that we succeeded in getting some values. So we're not fully satisfied with it, but sometimes the orba were pretty large. But at least this shows the feasibility of trying to get the physical vibration from the orbit. And actually, we do have some work. We're still working actually on that. Right. So we get these interesting values, but we also found our results basically were more or less compatible with homogeneous interior, but we found some strange behavior in the residuals that in practice showed a possible mismodeling of Saturn's gravity field. So when you are solving for the physical parameters in your system, you are solving for initial state vectors, physical vibration, masses, but also other stuff like Saturn's gravity field and so on. And you want to be sure that the gravity field of Saturn you get is reliable and makes sense compared to what Cassini is telling you, because Cassini gets a much better gravity field of Saturn that you can expect to get with inner moons. And one of the reasons for that issue was probably the fact that so far we are using ellipsoidal theoretical figure when we are trying to get the center figure of the satellite. So here, this is 4 examples of the inner moons where I do see the images here. This is once again the ISS data, and here you can see in turquoise, turquoise by the way in French, you can see here the expected shape. So this is what we are computing, and you can see that the real shape is different. Of course, it's not an ellipsoidal shape. Here we use the SPICE ellipsoidal shape, and probably one of the reasons here is that we are so much accurate with the ISS data that we definitely need to have a better modeling of the shape of the inner moons and just ellipsoidal shape. So we did a lot of work on that this last several months. So I will not present that at the moment, but if you have questions at the end of my talk, I can definitely tell more about what we are doing. Okay, so another example, probably, I'm just looking at the clock. Okay. Another example of what we can do is classical astrometry. One of the things is now once again related to tides. So now let's look at tides raised by Titan on Saturn. So So once again, the same idea. You have tidal deflation of Saturn. And you probably would like to measure this quantity, because if you can characterize the tidal displacement, then you get interesting information about the interior of Saturn. So unfortunately, Cassini could not provide an accurate and precise value of the love number of Saturn. And but fortunately, we succeeded in doing that with classical astrometry. So this is the kind of measurements that finally actually was possible thanks to classical astrometry and ISS data with radio science. So how did we succeed to do that? Actually, I would have thought 10 years ago that would be impossible to get the tidal deformation of Saturn. So let's call it the love number. So if you have questions about that at the end of the talk, once again, I can say more. So called love number K2 in this case here. So I would have said it is impossible to get the tidal deformation from the orbit of the moons, whether the inner moons or whether the main moons of Saturn. I would say no, the signal is very small, and it's very small. But the cool thing with the Saturn system is that you have co-orbital moons. So you have two co-orbital moons with Tethys that are called Telesto and Calypso, and two co-orbital moons of Dione that are called Polydeuces and Hélène. And very interestingly, let's look at that. You have, let's say, you have here, let's say, Tethys that is raising tides on Saturn. And you have here one of the co-orbitals, so let's say Telesto here, actually that suffers, of course, all the gravity of the gravitational interaction, so the other moons, material perturbations, and so on, but is also suffering because of the potential here related to tides. So basically, it suffers a deformed Saturn because of tides. So the signal is very small, but here in this case here, it's not a periodic signal, it's a secular one. So permanently, actually, the force acting on Telesto here is not directed toward the center of Saturn. It's slightly shifted because of the tidal bulge. And thanks to that, so this very specific configurations, the real geometry, co-orbital moons, you are in the end very sensitive to the tidal bulge raised on Saturn. And thanks to that, we were able to determine the love number of Saturn really precisely, I think. So I think it's pretty good accuracy, actually, for our first estimation. Right, so sometimes it's tricky, and sometimes you have good news, and that was definitely pretty good news for us. What you can do with the love number now, then, is to do some interior modeling of Saturn and making different assumptions about the composition interior, the stratification, and so on, the rotation of the interior. And in the end, you may compare the love number that you get from your modeling with the love number that is observed. And this is the work that actually, especially Tristan Guyot and Gabriel Tobé did, with also Stéphane Matisse and Françoise Rému here, and they basically used the number that we had from classical astrometry, and they were able to discriminate. So some of the moldings that were not compatible with the value we get. So we get here an example here. What in that case, actually, the error bar is still probably a bit large. So we still say that most of all these models work, but we are able to remove some of them. And of course, the idea is that if we can improve the measurements or by adding more data, or if we can reduce the data with better algorithm, we should be able to discriminate way more between all this interior modeling. So this is something that we are working on also, and we have also some good reason to think that we can definitely improve this estimation. Okay, maybe my last example here, but what you can do with astrometry, relating now to tidal dissipation. So I would just like to give you a bit of, let's say, history of the way we're thinking about the Saturnian long-term formation and long-term evolution. So tides, actually, if you remember the case of Phobos, I told you that Phobos is going closer and closer to Mars, and eventually it will actually, it's already pretty close to its rush limit, so it should not survive. That's typically 40 million years. So the idea is that tides are very powerful for displacement of the satellite. So with time, when the satellite here is revolving closer to its primary, it's getting closer because the tidal bulge are delayed in direction with respect to the satellite. So this is the case of Phobos. When you are on the other hand, when you are revolving with a period that is lower than the spin of the planet, then the tidal bulge lag in advance. And in that case, you are getting further from the primary. So our own moon typically is getting further from the Earth at a rate of 3.8 centimeters per year because of the tides it raises on the Earth. So for most of the moons, actually, were in that case. So they are revolving slower than the spin of the planet. And Goldreich and Thoder in 1966 used this observation to provide some kind of constraint on the tidal dissipation in Jupiter, Saturn, and Uranus. In the case of Saturn, they used Mimas. So they said, well, we do know where Mimas is at the moment. So we know its distance from Saturn. And they said, we do know where is the synchronous orbit. So since we know the spin of Saturn roughly, we do know what is the minimum distance to Saturn where Mimas must have formed. It cannot have formed closer because then it would have gone in the other direction and crashed on Saturn. So by doing that, they were able to provide an average value of this quantity here that is related to the amount of energy lost by friction by tides in Saturn. But they had two strong hypotheses here. They assumed that Mimas formed 4.5 million years ago, and they also assume that this amount of dissipation in Saturn by tides is roughly constant. So it doesn't change with time. It doesn't change also with tidal frequency. With time, actually, these two assumptions actually were slightly debated. So the first one, from Chandos et al. 2009, yeah, sorry. They found that Mimas had 90% chances to be destroyed by the late heavy bombardment, meaning that Mimas may not be 4.5 billion years old. And concerning the interior of Saturn and tidal dissipation in Saturn, people from stellar physics applying their method to giant planets, suggested that dissipation in a giant planet may be very different from what you get with the Earth, for instance, or for Mars, or telluric planet. And especially, dissipation may be very sensitive to tidal frequency. But basically, this Goldreich and Thoder 1966 paper was really the reference for decades, and it really strongly it provides strong constraint on our vision of such a system formation for a long time. And in 2012 and 2017, actually, we showed using this astrometry, so using actually more than a century of data, we found that the rate at which the main moon of Saturn, at least 4 of them, was changing was really different, and definitely much faster than what was expected from Goldreich and Thoder 1966. And so I think in 2017 we provided 2 different estimations. One, I think, the red error bars with the values I got at the Paris Observatory, and the green one was the value from Bob Jacobson and JPL. And we showed that basically tidal dissipation is at least an order of magnitude stronger in Saturn than what was expected. And roughly at the same time, Fuller et al., the Caltex, provided an interesting explanation for this point here on Rhea. You can see that Rhea is really off from the other guys by what he called resonant log mechanism, meaning the fact that tidal dissipation in general planet is very sensitive to tidal frequency. But now, if for some reason this sensitivity to tidal frequency changes itself with time, then you can have a very different behavior of the orbital expansion. So that was basically what they said. And actually, very interestingly, in 2016, they said that if the model was correct, this resonant clock mechanism was arising inside Saturn, they would have expected to have a very strong signal on Titan, so a very strong expansion of the orbit of Titan, much faster than what was expected from classical tidal theory. And here we arrive in 2020, where we basically used as much as data as we could from Cassini spacecraft or classical astrometry. Of course, also with all the data, so HEST, ground-based observations, photographic plates, heliometer, micrometer measurements for more than a century, because we are looking at orbital expansion, so we want to have a very large time span of observation, because this is a very long periodic variation. And we get this error bar, this value here in purple, and you can see that we worked also, thanks to our collaboration with Paolo Tortora and his team, we also were able to provide an estimation of Titan's orbital expansion using radio tracking data only. So using just the flybys of Titan by Cassini over more than 10 years of data, and we're roughly providing consistent results showing that Titan was going much, much faster outside of such a system than what was expected. And the other measurements here were in agreement with what we published before, but with slightly smaller error bar. Now, what is very interesting is, as you can see, this blue bars here was predicted, and these values here are what are the values expected from the tidal log mechanism of James Fuller. So this diagram, from using a lot of as much data as we could, clearly showed a pretty good agreement between this new kind of tidal model from Fuller et al. And the data, the best data we get. So I think this is very important. First of all, because it shows that tides in giant planets, at least in the case of Saturn, but there's no reason to believe that Saturn is an exception here, can be very different from the way we model tides in the Earth or the Moon, for instance, or Mars. So I think that's very important, especially when you have giant planets and Saturn-like or Gemini-like exoplanets. You can also wonder if in the case of Jupiter, you might get the same kind of physics. At the moment, we do not know. This is definitely something we are looking for. It's a bit more difficult for some reason in the case of a given satellite, because of you have the Laplace resonance. So it's not easy to separate the signal because everything is correlated. But this is something definitely that we'd like to assess. Right, so I think it's time for conclusion. I think I'm roughly on time. Once again, space geodesy and classical astrometry are extremely complementary. This is really something that for me is pretty clear, and it's very important that the two communities really get close. Also because the method also are pretty close. So I think it's very, very important to keep in mind that they are not that different. They are not doing things that different than what we are doing. They all evolve very fast also. In both cases, actually, I'm working on JUICE, and the accuracy you can have with radio sense measurements is absolutely fantastic. If you compare that, for instance, with the Galileo measurements that we had in the 1990s, well, clearly this is really, really different. So in a few decades, actually, the improvements were really strong. This is the case also for classical astrometry. Now, if you have in mind the Gaia catalog and the star occultation, well, in that case, really you are one or two of those magnitude better than what you were able to do just several years ago. And the Cassini mission provided excellent results with astrometry, and I think it's really a show window of what classical astrometry can do when it's at its best with great data. It really can bring a lot on our understanding of the system, and increasing scientific exchanges generally, especially in the case of a space mission, is very important and benefits to everyone. This is definitely the case for the JUICE mission or Clipper mission that actually should arrive at the same time in the Jovan system around 2029. And in that case, I know that Brazil observers are extremely motivated and are extremely gifted for providing high accuracy data on this kind of moons. And definitely, I'm glad to be here and actually to work with them, because I think they're very important. And the more we get together, we can work together, and the best we can get from great result we can get from this kind of missions. So that's it for the moment. I haven't talked much about what we are doing at the moment. We are doing stuff, but I do not have any slides really. But I guess you may have questions, and if you want to know a bit more, well, just ask questions or send me an email. Thank you.
Okay, Valéry, thanks very much for the great presentation. So now we are open for questions. If someone would like to make a question, could write on the chat. I can call you or raise your hand, or just open your mic and say your name. Okay, so Tamiris, you may start.
Hey Valéry, thanks for the talk. About the liberation frequency, you say that that is feasible to measure it, but it's difficult at the same time. Can you highlight the most difficult to get this frequency, to obtain this frequency?
You mean physical liberation?
Yes.
One of the reasons definitely is if you're looking at the error bars I provided. Yes, you see my slide? Do you see my slide? It's okay?
Not really. I don't know if it's mine.
No, it's not. It's showing your full screen.
Ah, so it's okay?
No.
It's a piece on the corner.
Ah, sorry.
Okay. Just you stop the presentation and start again. Just the presentation.
Okay.
Yeah, I think it's easier.
I will do that. Yeah. Yeah, sorry. Yeah, it should work now, right?
Yes.
Okay. Okay, so you can see here, so the error bars here, generally speaking, are large. So this means that this is the uncertainty that is large. It's too large. One of the reasons for that is that for doing this kind of measurement, we are assuming that we do know the gravity field of the moon. So basically, we assume that we know the C20 and C22. And from that, we are inferring the physical vibration. So this is what is done here. I'm assuming a specific gravity field of the moon. And I'm assuming that from the assumption that it's homogeneous. And from that, I can look at the physical vibration I get from the data. And I can compare that with what is expected if that's truly homogeneous. If that's not homogeneous, in that case, I should have a disagreement. But most of the issue here is the error bars. And the error bar here is of course, partly coming from the uncertainty on the astrometric measurements. And in that case, definitely here, improving this kind of shape is very important, because you do typically the residuals on the inner moons are 3 times worse than the main moons of Saturn. So you do have a factor of 3. And it's 3 times worse, essentially because of the shape you see that is completely wrong. The other reason also is that our knowledge of the volume of the moons is actually, at that time, was probably not that good. And if you do not know extremely precisely the volume of the moon, then you may have some uncertainty on the C20 and C22 when you are assuming, even though you are assuming they're homogeneous, you still also have to know exactly its volume. But since you have uncertainty on the volume also, that increases in the end the error bar you get here. So in short, improving the astrometry on one hand, but also improving estimation of the volume on the other hand, should allow us to have a much better, smaller error bar. So in that case, I should say that for this issue here, it's solved on our side. So we're working with Nicolas Rambaud here and Nick Cooper, and we did a lot of work here to get to introduce the shape of the inner moons into Caviar, which is the software we're using. So now we have a really good fit, a pretty good match between the projected shape and what we do see on the image. So now we have much better much better measurements, but also we have much better volume of the moons, and so we also should get much smaller error bars. So I do not have any final results to present here, but just to tell you that we do have much better result at the moment. So yeah, so I'm very enthusiastic about the fact that we should be able to get something reliable within probably, well, I guess 2 months probably.
Thank you.
Okay, ladies. Anybody else? Well, I have a question. Well, actually, you touched the point, but didn't say much about the resonance between the satellites when you measure the migration. How can you improve that using, let's say, models of migration associated to the resonance? So, for instance, that is, if you measure how they migrate and how should be, since you have this resonance, how could
Well, that's a good question. Yes, you are correct. But resonances, sometimes they are not a good, well, sometimes are a good thing, like the orbitals. Orbitals was really fantastic for love number. Sometimes they are not good, they are not your friend, because as I told you, you have correlations, and you're absolutely right here. But you have also other moons that are also in resonance that can come in the end to be your friend. So here you do not see it, but in the modeling, we also used Methone. And Methone is a very small moon that is in resonance with Mimas. So you may say an extra moon in resonance. Well, but the good thing is that Methone is so small that its mass doesn't matter. So basically it just suffers gravity, but it does not introduce gravity. So thanks to Methone, you are able to get extremely accurate value of the mass of Mimas, and also a high accuracy on its motion. So thanks to Methone, really, it helps a lot, despite the Mimas status resonance.
I see. It's
so sometimes resonance is your friend.
Yeah, it's following the same approach of the orbitals. Yeah. Okay.
Yes, absolutely.
Good. Okay. Very, very interesting. Okay. Anybody else? Any more questions or comments? Oh, we have here Bruno Morgado, please.
Hi, Valéry.
Hi, Bruno.
So, can you talk a little more about JUICE and Europa Clipper and how the astrometric data will improve the knowledge for the Galilean system?
Yes, that's very important. So, yeah, so the news definitely is the fact that Clipper will not be there before JUICE. So just from a very practical point of view, as you know, you want to save propellant during maneuvers, and during orbit insertion, definitely would like to know very accurately where the moons are. Because if the ephemeris is wrong, then basically you will need to use more propellant. And so in the end, you may not be as much ambitious as you would like to be. So you cannot here in that case expect that the Clipper will really nail down the ephemeris of the Galilean system, because it will arrive at the same time. So for both missions, it's very important to have accurate astrometric data, even more than before. So from the propellant side, this is probably evident. The other thing is that for Clipper and JUICE, as you know, there are no IO flybys. So this means that you're not going to be very accurate on IO. Having said that, you may have heard that the Juno spacecraft may get flybys of some of the moons, and especially IO. It may get 2 flybys of IO with very high accuracy. So probably in that case, despite the fact that Clipper and JUICE will not have IOs flyby, you may still get some good constraint on the IO. But for Callisto, before orbit insertion, and even for the other moons, definitely you should really have a classical astrometry there. So for saving propellant, definitely that's very important. For physics, I would say it possibly differently. It's possible if you are considering Fuller et al. So as I said, he said that for Titan, he was expecting a strong orbital expansion. But this is also the case for Callisto, if we do have tidal mechanism in Jupiter. So at the moment, we are not very far from being able to constrain the orbital expansion of Callisto, but we are still lacking some data and some very accurate data. So one possibility is to, of course, reduce the data, the old data using Gaia and so on, maybe going to the old eclipses and so on. But also definitely which should be done, I think, is to do some star occultation of Callisto in priority, and to get a strong constraint on Callisto's orbit at modern epoch. Last, once again, radius science provides you center of mass. Classical astrometry provides center of figure. This means that even if you're going to have JUICE and Clipper, and that will provide you strong constraint on the orbit of the moons, I think that having star occultation, for instance, or radar measurements will definitely provide valuable information if we want to assess center of figure, center of mass shift. And that won't be able to do that. I mean, we will not be able to do that for Callisto, for IO. We for sure should be able to do that for Ganymede with JUICE, and I'm guessing probably with for Europa with Clipper. But at least for IO and Callisto, the best way to do that is star occultation on one hand and radio science on the other one. So Callisto star occultation are going to be very valuable.
Thank you.
Okay, Bruno. David Nesroni, do you still have a question, or did you change your mind?
I did. Yeah, I'm not sure, but when Valéry was mentioning these moons that can be your friends or can be your enemies, right? When doing this science, I thought a moon that can be your friend could be Hyperion, right? Hyperion is in the 4-3 resonance with Titan. It's a very small body, so hopefully it shouldn't affect the fits. And it has so it's in the resonance, and it has like 0.1 or 0.15 eccentricities, which presumably was excited by the resonance. So you could play a game, taking your tidal model, moving Titan out, and see if you can generate that orbit. You know, there are some conditions that Hyperion should skip over the outer resonances, but should be captured into 4-3, which might require some special rate, and you could get, you know, additional constraints on what's going on, but I think it should work. It should work. Yeah.
Yes, actually, so you are correct. So one way to, if you want to explain, I think there are works published already on that matter that say that if you want to have the 4-to-3 resonance with Titan, you need to move Titan. William Polycarp actually did a similar work more recently about Iapetus, where he tried to explain the inclination of Iapetus with a possible resonance crossing with Titan. And we tried actually to figure out if Titan would be able to do something. And the conclusion was that tidal dissipation in Saturn should be significant, if significant, should indeed provide some kick on the inclination, somewhat in agreement with what we are seeing today. So I think his constraint was pretty large. So he said it should be between, I don't want to be wrong, should be, let's say, it could be a few tens, few hundreds, but not more than few thousands or something like this. So definitely said dissipation in Saturn should be significant, but he was not able to say really more how much. So yeah, same idea, you're absolutely right, yeah.
Okay, sounds good.
Okay, thank you.
Yes, the paper published on that, he published that 3 years ago.
I think I have seen the paper. As for the Hyperion paper, I know that there are publications in the past, but given that Titan was thought not to migrate too much, I wonder how those works, like, you know, excited. They must have placed the moon really close to the resonance and then around Titan a little bit. Yes.
Yes, you're right. I think Matthias Schuck submitted a paper exactly on that.
Okay.
You may find it on archive, but for some reason I think it was not accepted. I think I don't know exactly the reason. Possibly because it was already more or less suggested by former papers. But you may find it on archive, I think. So yeah, and it was doing exactly what you are saying with the strong dissipation in Saturn.
Okay, thanks.
Thanks, David. So anybody else? Marcelo, please. Marcelo Sapin.
Hi, Marcelo.
Hi, Valéry. How are you doing? Nice talk. I have a question. If I understood it correctly, the Saturn's atmosphere may play a more important role in the tides of Saturn tides than expected. Is that correct?
Well, it depends what you mean by atmosphere. I would say fluid physics is more important. So yeah, it's not the upper atmosphere. It's really in the interior, but it's the fact that it's fluid and not a rocky body.
Okay, so connect with that. Is there some clue we could get from this hexagon? The polar hexagon in Saturn, I mean, this is not seen in other gaseous planets, but in Saturn we see it, and there seems to be some very specifics to produce this kind of shape in regular, constant shape. So this might indicate that there are some different things going on in the dynamics of the atmosphere that could support perhaps some of these later findings.
Yes, as far as I know, I think this is very different physics. So I wouldn't say that it's related to tides, but you are correct. It's a very interesting feature that we do see on the pole of Saturn. I think northern pole of Saturn. Yeah.
Okay, thank you.
Thanks, Marcelo. So Nelson.
Hi, Otto.
You have a question?
Yes,
Hi.
Please. Thank you. Hi, Valéry. I'm Nelson Talegari from UNESP. Very nice talk. I have a question on the. I'm motivated to do this question, to do this answer to you, because in your abstract, you are you refer to the small, recently discovered satellites, no? And talked about the anti-meton and the other very small satellites. So you have a table when you show the geometric measurement of the physical vibrations of epimeters and genus. No? I try to understand if it's possible to have a similar measure or kind of this for these very small particles, small satellites. I'm reading on these topics, and then I'd like to talk to you. Thank you.
Yeah, thank you. That's a good question. Yeah, so if you are looking here on this slide here, I showed you the estimation of the mass or the density of the 5 moons, Atlas, Prometheus, Pandora, Epimetheus, and Janus. But when I was showing, so sorry, if it maybe up. Oh no, my gosh, I did something wrong. Okay, you see my slide again?
No, we see your full screen. Yeah, now you see. Yes.
Okay. Sorry. So here in that case here, I do not have Atlas, and the reason is if the moon is too small, then the feedback from the radiation on the orbit is a smaller signal. So in the case of Atlas, this method doesn't work. It fails, despite the fact that Atlas is closer to Saturn. But it fails because it's too small. So ideally, you would like to have a large moon pretty close to the primary and pretty elongated. So in the case of Anti, Methone, Palen, they're just too small. Even for Atlas, that doesn't work because we do not have accurate enough data. You should probably have an order of magnitude more accuracy on Atlas itself. So no, it won't work.
Okay.
But it may work for MIMAS. And MIMAS is definitely a fantastic target for the future because applying this method to MIMAS is still big. It's bigger. It's not that far away. It's not as distorted shape, but still, it's still significant. So in the case of MIMAS, this is the satellite we're looking for because it will be very interesting to get its physical vibration from the orbit the feedback on the orbit, because that may allow us to discriminate between global ocean and elongated core inside MIMAS. So this is really our final goal, really, is to go to that result for MIMAS. But so you should go for bigger moons, but not smaller ones, unless you get much better data.
Okay. Anybody else? Any more questions or comments? So I think that's it. Thanks very much, Valéry. I think it was a wonderful presentation and a lot of interesting things to discuss.